Alright, let's start today's webinar. First of all, a warm welcome to everyone who joined. My name is Niels Verdek and I will be your host today. For today's topic is the experimental validation of an optimized CPU cooler. It's quite a bit of an odd one, seeing as we mainly focus on the simulation aspect. But for today, we'll also cover experimental results. The CPU cooler has already been covered in a previous webinar, where we mainly focused on the design aspects and the design for additive manufacturing. But as I said earlier, it's more about the experimental validation. All right, so in today's webinar, we'll briefly introduce what generative design is and how it helped us optimize this particular design. And then we can dive deeper into the experimental results. At the end, we'll have a Q&A session. So if you have any questions throughout this webinar, feel free to put them in the chat box. Our moderators are following the webinar and will already answer some of those questions. And any unanswered questions or very interesting questions, those I'll cover at the end. And let's try to keep this within the 30-minute marker. All right, but let's start with the beginning. What is generative design? In our views, generative design is a linearization of the design process. While on the left side of the screen of the slide deck, you'll see the conventional design cycle, where you start from the geometry, you create a first CAD model, you run some CFD simulations, or you will do physical experiments, post-process the results, and loop through this until you get a solution, which is a very manual effort. It takes quite a bit of human engineering time to get to just a solution. With generative design, as I said earlier, we really want to linearize the process and relieve as much of the human engineering time, or reduce the human engineering time as much as possible. So again, we'll start from an empty geometry. The users will fill in some information, and that's it. From that on, everything is completely optimized, where ColdStream will run through hundreds and hundreds of design cycles to get to the best possible solution for the application at hand. I said the human engineering time is really reduced. And what does it look like? Basically, these are the only steps that are required. You upload your geometry, you fill in the solids and fluids, basically what are the boundary conditions, what are the physics, then setting the boundary conditions themselves. So what are the inlet conditions, the outlet conditions, what does the heat load look like. The only new thing compared to other CFD software is you have to set targets and the design volume. The design volume is the volume where ColdStream is allowed to modify the geometry, so basically to add the optimization structures. And the targets that ColdStream want to optimize for, be it maximize heat exchange, minimize pressure drop, constrain the power dissipation, etc., etc. That's the only input that is required from you. Everything else is completely automated. And then it starts with the actual generative design cycle. There are multiple optimization techniques that can be used. The one you'll most likely be familiar with is parametric optimization, where you a priori define a given design philosophy. For instance, here it's a pin design, so we look at the top, and then you basically parameterize that design philosophy. For a pin design, you have a given diameter on the pins, spacing between different pins, and then it's not visible on the screen, but then the length of the pins, and you basically optimize those parameters for your application. It's very simple, but as you can imagine, it's most likely not the most optimal solution. And then there is something called shape optimization. With shape optimization, you initialize a given optimal solution or given design, and then within shape optimization, the boundaries, so the shape of your initial design is further optimized. It's much more complex, or the potential solution is much more complex than what you can get from parametric optimization. So inherently, it's more optimal, but the eventual optimal solution is very much dependent on your initial condition. So it's not fully optimal. With generative design, the software really has to start from scratch, and it can fully autonomously determine where in the geometry material needs to be placed and where not, which of course allows for the most freedom and thus will return the most optimal solution to your problem. What does the actual algorithm behind look like? So with your targets, you define your objectives, for instance, minimizing the temperature over a given volume, and which is subject to constraints, both performance constraints like the pressure constraint, but also manufacturing constraints. I'll come back to that later in the next slide. And then you basically parameterize your geometry. You perform a CFD simulation to get the performance value. You evaluate the performance the cost function, so the performance. For instance, your temperature over a given volume. If it's okay, you're ready. You can export it to CAD file. If it's not okay, you do a sensitivity analysis, and that's really much that's very much the most difficult aspect of the conventional design cycle. With sensitivity analysis, you basically determine, if I change that, how much will that affect my cost function? And after your sensitivity analysis, you will adapt the geometry to have the best possible, or to have the biggest gradients, the biggest possible change, or the biggest possible reduction in your cost function. Based on that, you update your design, and then you loop through it. You again perform a CFD simulation and evaluate the performance curve, and that is completely automated within generative design software. All right, I mentioned manufacturing constraints. In this particular case, we optimized, or we designed for additive manufacturing. So a priori, we assigned some manufacturing constraints. For instance, what is the overhang angle? What is my resolution level? Well, so basically, what is the printing resolution of my machine? What are the unsupported lengths that can be supported by a machine, etc. And those are a priori given before ColdStream runs through its design cycles to make sure that whatever ColdStream returns is fully manufacturable. All right, now that we know what generative design is, we can apply it on a case study. And as you know from the title, we'll cover a CPU cooler. So basically what we did is we bought a commercial off-the-shelf component, quite an expensive one. We took it apart, as you can see here, where we noticed that the conventional design is basically skived fins, so very narrow fins, and they are very closely spaced. And that's something that we then redrew in CAD and let it optimize by our software. Perhaps I'll cover it in ColdStream itself, makes it a bit more visible, or makes it a bit more clear. Yes, so you should be able to see ColdStream now, or the projects tab of ColdStream, and that's the main landing page. Sorry, after you log on to ColdStream, where you have an overview of all your different projects. But here we'll go to the liquid CPU cooler. Yes, and then I'll expand this. Yes. So within your projects, you have all your cases, as you just saw. So all of your different engineering problems that you want to solve, either simulations or fully custom designs. And once you create a new case, you can upload your geometry. And this is the geometry that we read through, basically the CAD that we made based on the conventional design. So we have a copper cold plate without the conventional design. We specified a design region, so only within this volume is ColdStream allowed to modify the CAD geometry. We have a housing surrounding everything, a heat source. We found online that the commercial product cools down or it can be applied to cool down an Intel chip, where we specified some boundary conditions, so a heat load and a target to minimize the temperature. and then we have a coolant to cool down everything, which is water glycol with an inlet and an outlet patch. All right, and as I said, we'll optimize for 3D printing, where copper will be used for the material that will be added within the design domain. All right, so once all that information has been filled in, the generative design cycle, the generative design software will take over, and after a short while, you will be able to look at the results of that optimization. And that's it. That is. So everything in green is a material that will be added, or that was added by ColdStream. In and by itself, it doesn't say much. I have to agree. But if we look at the fluid domain, and perhaps color it a bit more clearly, yes, we can more easily see what the design philosophy is that ColdStream went with. So we have our inlet in the center and our outlet on the right. And I can easily see that the first or the middle part, where the fluid enters the design domain, is mainly used to help distribute the flow over different channels. And those channels are then used to cool down the Intel chip. And at the edge of the domain, that is really used to help collect the coolant and redirect it towards the outlet. A very clever design, if I do say so myself, that outperforms the conventional design quite a bit. And by how much, that's perfectly summarized within this slide. So on the left, you see the conventional design, so the sky fins, and on the right you see the thermally optimized design, and where we're looking at the base plate or the copper plate together with the design philosophy itself, and it's colored by the temperature and all on the same scale in Kelvin here. So you can see on the left a very big, a very broad temperature range, while on the right with the optimized design, it's almost uniform. And if we look at the key performance values, we see that the temperature has decreased by 55% compared to the sky fins, and the temperature uniformity, as can be very plainly see from this color scheme, is increased by 8%. So the temperature is much more uniform in the optimized design compared to the conventional design, and that for an equal pressure drop throughout both designs. All right, so ColdStream optimized this, and then we send it to our 3D printing partner, Novis, and they printed the part in real life, as can be seen here on the bottom right. Now that we have a design, we can finally look at the experimental validation. So at Diabatix, we continuously do, we continuously set up some experimental validation projects just to make sure that whatever ColdStream delivers does meet the reality. And we have two objectives for all of those experimental validation projects. First of all, it needs to be objective, and it needs to be qualitative. With objective, we mean, of course, we don't want to influence our own, or we don't want to have our own influence on the design. And qualitative, whatever experimental validations that we do, that it's qualitative, that the performance of it is of a high standard. And because of those two objectives, we work together with third parties, either local universities here in Belgium, like the University of Ghent or the KU Leuven, or with research organizations like NLR in the Netherlands or Vlaanders Make. For this particular project, we work together with the KU Leuven, and luckily they are already testing some heat exchangers of their own. As you can see here, they're gyroid heat exchangers, and we could use their setup. And basically, they designed a plug-and-play system, so the gray part here can be plugged out, and our own system can be inserted. The downside of this, of course, is that we have to make use of their equipment and the boundary conditions that they set. So we designed for a water glycol coolant, while in their physical setup, distilled water is being used. The pump itself could also not reach the flow rates that we designed it for, the 0.82 liters per minute. in the physical experiment, or in this setup, the flow or the pump itself could only reach a maximum of 200 milliliters per minute. So it's a bit of adaptation. We had to adapt to their setup, and in order to do that, we had to rerun. We had to rerun some simulations with the optimized geometry to make sure that whatever we compare to the experimental validation, that we have a like-for-like comparison in simulation. And let's have a quick look at what the setup looks like. Yes. First of all, you will notice quite a big addition in regions. And the biggest change, I would say, is the heater element. Is the heater element change? So originally, it was designed for an Intel chip, an Intel 1700 chip. Well, in the real experiments, we'll of course not just buy that chip to solely be used in the experiments. We'll use a conventional resistive element. And that, of course, has different dimensions compared to the Intel chip. So we have our heater. In order to somewhat get to the same base geometry or the same geometry as the original Intel chip, we also placed a small copper heat spreader to help distribute the heat from the smaller resistive element to have the somewhat the same profile as the Intel chip. Alright, the heatsink base, that remains the same. Then we have our optimized structures from earlier. We added a bottom geometry to make sure that everything can be screwed together and to not have any leaks. The housing on top is is made a bit more robust to allow for thermocouples to be added, etc. But everything else is exactly the same. So our coolant domain is the same, our inlet and outlet patches remain the same. We just added some more regions to match as close as possible to the experimental setup. Alright. So the geometry that you saw on ColdStream, that will then be plugged into this system. And now we can have a look at the raw data. So on the screen here, you will see the temperature of the heat source. And you see that both for the experiments in red and the blue line of the simulations. And the first thing that you will notice, there's a very bad agreement between the two, especially at the higher flow rates, where there's a 50% error margin between the two. When we had a closer look at the results of the experiments, we see that the heat imposed, there's quite a bit of heat loss in the actual experimental validation, or during the actual experiments. In the dotted line, you will see the heat load that is being applied to the heater itself, and in the solid red line, you will see the heat that is being evacuated through the outlet of the coolant. And you will see that for the higher flow rates, the difference is not that much. There is a small difference, but it's not that great. And the lower the flow rate, the bigger the difference between those two lines, which of course makes sense. The lower the flow rate, the more each of our coolant elements and the coolant molecules have to capture the heat, the higher temperatures, and thus the easier for the heat to escape to the environment. If we correct for that, we see the following: the temperature difference at the higher flow rates is still quite significant, and now the temperature difference at the lower flow rates has increased. So at first glance you will say that's not the solution, and I tend to agree. But the main benefit, or when we look at the graph itself, we see that temperature itself across all flow rates is quite constant, which is very interesting. A constant temperature difference for different flow rates lets us believe that, or makes us believe that there is some thermal resistivity from the conduction part, in the conduction part of the case setup or of the geometry. And if we calculate the thermal resistivity, we have noticed that 1.8 microns of air, so a small air gap of 1.8 microns, can already accommodate for 1 degree in heat up, which is exactly what we see here. The average temperature delta is 0.8 degrees. So already little under 1.8 microns can accommodate for a 1 degree heat up. In the simulations, we assumed perfect contact area. Well, of course, in the real experiments, there will always be some air gap. And if you accommodate for that, we see an excellent match between the experimental results, the red crosses, and the blue simulation data. All right. If we then go to the summary, or if we summarize whatever we discussed here in the webinar, we first covered what generative design is and how it can be used to design for additive manufacturing. And we then applied that to a case study of a CPU cooler. And then we noticed, or then we saw that ColdStream can return a design which is 55%, which has a 55% thermal improvement, while keeping the pressure drop equal, and it has an excellent match. And whatever ColdStream returns has an excellent match with the experimental results. All right. Do you have any questions? I'll have a look at the chat box. The first question comes in, why don't we discuss anything, or why don't we show anything about the pressure drop? Excellent question. So in the experimental results, we only covered the temperature and not the pressure drop. You heard me mention that the pressure drop is that pressure drop is equal for both the conventional design as well as the topology optimized design, but we never validated it in the experiments, and there is a very good reason for that. Basically, in the setup itself, there were no pressure sensors. That's the only reason why we didn't look at the temperature, the pressure drop. There is one, or the setup itself did right away the effort of the pump, but there are quite a bit of losses in the pipes, etc. So comparing that to just a pressure drop between in and outlet ports of our heat exchanger, that won't have that big of an impact. So that's basically the only reason why we didn't look at the pressure drop. All right. I hope whoever asks that question that it's okay. That answer is satisfies you. Next question. What are my thoughts on gyroids? Yeah, that's a very interesting question. My thoughts on gyroids. If you purely look at the heat exchange of gyroid geometries, that's very good. That's very clear from the literature already. But pressure drop wise, it has quite a big of a pressure drop. If we're honest, so for heat exchangers to solely rely on gyroids, I think there are other solutions that are better. Basically, the penalty for pressure drop is a bit too high in my opinion. All right. Given the interest of time, I'll leave the Q&A, or I'll close the Q&A here. Don't worry, the moderators will still answer the questions in the chat box. So if you have any, feel free to put them there. And we'll then move to the end of the webinar. So throughout this webinar, or the basis of this webinar relied on the design of ColdStream itself. But you can try ColdStream out for your own by following this link. So you will get access to the ColdStream viewer account, where you can have a look at all of our finished demos. Or if you want to know more about what Diabatix and ColdStream can do for you, feel free to reach out to me feel free to reach out to the team, by emailing to this link or basically calling this phone number. All right, that brings us to the end of the webinar. The only thing left for me to do is to all wish you a very pleasant day still, and I hope to see you soon in a new webinar. Bye bye.